Professor Sen already joined here. Uh, Dr. Sen, you are muted.
Oh, yeah, I'm here.
Okay, great.
Yeah.
So, how are you, sir?
I'm just fine.
Okay. Are
Yeah,
you in office or are in
no,
the...
I'm at home. Yeah, I'm
Okay,
at home.
very good, very good. So, just Abhinay Singh completed his lecture.
Sure, sure, sure.
So, I would request to you if you want to take this, session to start early little bit so that we can get much more time and question answering or more informative knowledge. We can do that.
Okay,
We can get
okay.
that. Okay.
Sure, there's no problem from my side. Yeah.
Okay, great. Okay. So, good afternoon, everyone. We are lucky that we got Dr. Somaditya Sen. He's an associate professor in the Department of Physics, and I'm happy to share that I and Dr. Somaditya Sen did PhD in the same institute, Indian Association for the Cultivation of Science in West Bengal. Basically, he is my senior. Okay. So, after completing his PhD from Indian Association for the Cultivation of Science, today, when Dr. Rajesh Kumar was giving lecture about the Raman spectroscopy, I think Dr. Sen also was there. He is the one of the witness. He knows how actually Professor C.V. Raman worked in ICS Kolkata and actually developed the C.V. Raman spectroscopy. There is big museum also that. After completing Dr. PhD, Dr. Srimanta Sen went to US to do his first postdoc. Then he moved Taiwan. Again, he went back to US, and after completing almost 7-8 years postdoc in abroad, then he finally joined in our
Then
Department of
yes.
Physics at IIT Indore. He is working mostly in condensed matter experiment, especially magnetic materials as well as some alloy kind of materials. Today he is going to deliver his wonderful lecture on the subject of ZnO structure and electronic properties effect of doping. So let's see such kind of works what he is doing couple of years, almost 10 years from IIT Indore. I would request to Dr. Somaditya Sen kindly take this session and please deliver your lecture.
Thank you very much, Srimanta. Thank you for inviting me for this venture. This is a very nice venture that you have taken, and I must congratulate you for taking such a nice venture to inviting all qualified audience to this thing. So to this Karyashala. So before I start, I want to say a few words of my journey towards science. Actually, some of you, most of you are doing PhD, right? So must be very confused what to do next and other things. There's a moments in life which you can uh, be very nervous about your future, but believe me, if you keep on your strength and keep your strength such that your determination uh, is unshaken, I think you can achieve something. Okay. If not, whatever you are dreaming of, maybe somewhere which God will ultimately take you to. Okay. So let me share my slides. Uh, my talk will be basically on based on zinc oxide, but it's not limited to it because it will be overview. Can you see my? Everyone can see my. Uh,
Yes, sir. Yes, sir.
yeah. Oh. So when I started working as a doctoral student in cultivation of science, I was very excited to do some good research. But unfortunately, what happened, I experienced that my efforts are actually not 100% that I wanted to put. Mainly because of an Indian scenario where we cannot access most of the equipment that are there. Like Raman was there in ISCS, but it was either not working at some time or working, but only limited to some people. And then there was an operator person who used to do it. So believe me, doing research is something different. You have to really take the things in your hand, and means you have to spend time with the sample and the instrument and understand how the instrument is giving what results. It's not a black box thing. So experimental physics is not a black box thing. You cannot means physics itself is not a black box thing. It's not. Then it would have been a operator thing, and other sort of company job. It's not a company job. So similarly, in your career also, you have to understand what you are putting in your career. You will get the results as such. So what is the difference between research in India? Until now, we have progressed a lot. We get some access to some of the instruments, or major instruments like Raman. Most of us can go to the common Raman facility and work. At that time, there was nothing like that. XRD, the simple XRD, an operator used to be there, and we used to go and sit. We were not allowed to enter the room also. So there was a glass window. We used to see the samples being put, and then the data was delivered to us on a not on a small floppy drive. So this type of things were there. So now we have moved forward, and it is your duty to take it forward so that at one time you will realize, if you go abroad, how things work there. People go to the instrument and spend hours on one single sample, trying to understand what is going on in their samples. Okay, so it's very important. So again, I say that the talk will be on zinc oxide, how the structure and electronic properties are correlated, and what is the effect of doping. But this is not just zinc oxide. This is every material. Every material that is in the universe will have the same signs. Okay. So my group is known mostly for oxide materials, and we specifically work on semiconductors, ferroelectrics, and magnetic materials. And recently, I am a little deviated from magnetic materials because that same problem came. We do not have a magnetometer here, so we had to send the samples to USA. So my collaborator, he works on the samples and then sends me back some data. Although I keep on communicating with him, and after he gives the data, I keep on asking, can you do this one? Can you do that one? And then some good results come. But it's truly, I have spent about 8 years on a very cutting edge magnetometer. And then after doing that, I realized that whatever I am doing from here is not only peanuts, it's meaningless. So that is one of the problems of doing research in India. Okay. But don't be disheartened. Things will change, and we will all move forward towards a better future. Okay. So I believe what China is doing today, we can do it tomorrow. And the tomorrow is very close. Okay. So my focus is on simple TM oxides. This is zinc oxide, titanium oxide, copper oxide, nickel oxide, iron oxide. These are the very simple oxides. I have worked on some cerium oxide here because it is a very strong, it has a very high band gap, and it can be tuned hugely towards meeting ends in the application side. And but my primary focus is on barium titanate, lead titanate, and sodium bismuth titanate. These are titanate perovskites, and these have very strong ferroelectric properties. And also there are some rare earth manganetes apart from the titanates, and ferrites that I am working on. And also some nickelites and cobaltites are also in the plan, which will come next. Okay. Now, amongst the properties that I study here is they're mostly optoelectronic, transport, dielectric properties, ferroelectric properties, and magnetic properties. With a special interest, now it is coming up very in last 1 year. I have been working on this. Actually, not 1 year, last 2 years. There is some telecommunication problem which can be fed with oxides. Okay, so they are called dielectric resonator antennas, and I'm trying to explore those fields. It will definitely give us very nice telecommunication facilities. You know, some of our older cell phones, they use barium titanate dielectric resonator antennas, DRAs, and those are now replaced by thin films, but we can also explore what exactly we can do on these things, these modified barium titanates and other ferroelectric materials. And the last thing that we are now putting our a little bit of mind into is the protein nanoparticle interaction. We have several collaborators who are doing the experiments. So far, you will be amazed that the protein nanoparticle interaction has been a trial experiment. So nothing to correlate the protein structure to the nanoparticle structure, and why is it happening. Those parts have not really been looked into. So the structural correlation of the nanoparticles to the protein molecules is a huge field that we can travel into. Okay. Now, saying of this, I'll just give an outline of this talk today. I just introduced the oxide materials. There, I will briefly talk about the importance of zinc oxide, and then go to the structure and synthesis techniques that are used to make zinc oxide or any other oxide materials, correlation to the electric properties, and then the modification of zinc oxide by doping and co-doping. This term is very important, co-doping, and why you will understand during my talk, and the role of the ionic size and charge of this on the structure, strain, and the crystallite size. Okay. Now, here I want to tell you about the applicability of generally oxide materials, but zinc oxide is a subpart of it. The structural stability of oxide materials is very robust. Okay, so it has a lot of longevity in the so if it is not non-hygroscopic oxide, like lanthanum oxide is a hygroscopic oxide, it does not stay long for in nature. But any other things like copper oxide, or maybe iron oxide, or maybe nickel oxide. Nickel oxide also has some hygroscopic nature, but zinc oxide is pretty stable, and it can remain quite a long time in nature. Okay, so those are the structural stability. The structure remains, and it's the devices that you can make can stay for longer. Electronic structure, the oxides can be semiconducting, can be metallic, and can be insulators. Zinc oxide is a semiconducting material, but it can be tuned. So you can create defect states, and you can generate strain in the material to tune the band gap of the material. Okay, so these oxide materials are applicable in materials chemistry, medicine, agriculture, energy applications, biomedical sensors, biosensors, and optoelectronics is very well-known thing. Optics, electronics, catalysis, and environmental application. Even it is used now in IT, information technology. Now, what makes oxides very interesting is the effective interaction of the target molecules on the metal oxide surface. Okay, so there are lots of properties, functionalities which can be generated from these surface activated things. Okay, now why is zinc oxide particularly? All oxides are like that, but zinc oxide particularly has a huge possibility of creating lots of new functionalities, because it is very easy to create defect states which are correlated to the oxygen. content. Okay, so oxygen can get into the lattice and get out of the lattice due to the processing of the material, and also due to the materials, the other elements that you can generate into it, put into the structure. Okay, so those oxygen related defects and the presence of a foreign element into the structure makes these materials a huge ground to explore. And that's the reason why zinc oxide in the last 30 years maybe has generated means thousands of papers in the community. Okay, so looking at the structure, while talking about the structure, we see that zinc oxide can generally can be in three different forms. Okay, the most popular, most stable material is the Woodside. It has a space group of p63mc, and there are other less stable structures, but very interesting structures like the zinc blend, which is a space group of 4 F43m, and rock salt, which has a P1. These two are cubic in nature, the zinc blend and rock salt, while Woodside is a hexagonal structure. Okay. Now, let me give you a little bit of information here. That zinc oxide, the zinc is in the tetrahedral form. What does it mean? The zinc has 4 different oxygens which are surrounding its location. Okay, so it is bonded to 4 different oxygens. And the zinc ionic radii will be 0.74 angstrom. Okay, but however, if you put a little bit of pressure and if you can change the bond lengths or the bond angles, then what will happen? It may move to a rock salt structure, which is a cubic structure, which is I do not know how many of you know the sodium chloride structure. It's like a cube. You imagine a cube and put sodium and chlorine atoms in alternatively on all the edges, and you get a sodium chloride structure. The same structure, I'll show you later, is the rock salt structure. Okay. So by pressurizing the Woodside structure, you can lead to a rock salt structure. Now, the interesting thing in the rock salt structure is that in the rock salt structure, you have 6 oxygen instead of 4 oxygens surrounding a zinc atom. Okay. So when that is happening, the zinc is no more in the 4 coordinated state. It is in the 6 coordinated state. So the ionic radii of zinc has changed here. Okay. And similarly, the oxygens also in the Woodside structure, it is 4 coordinated. So its atomic radii will be 1.24, and in the 6 coordinated state, it will be 1.26. There's not much change in the oxygen, but yes, there's obviously a huge change in the zinc ionic radii. Okay. Now, Woodside is the most stable form, I told you already. And zinc blend is a very sensitive structure which can only be grown on a cubic lattice structure. Okay, so what do you mean by that? The cubic, if you have a cubic lattice as a substrate, okay, then only you can grow the zinc blend structure on top of it, because the zinc and the oxygen tries to imitate the cubic lattice structure. Okay, so and the rock salt structure, I'll come to it. Okay, before I go into the details, I just want to tell you that the structure is a very important thing. Okay, because here what happens, you have to understand that the lowest energy of formation is attained when you have a particular bond length or the particular bond angle in between the constituent elements. Okay. Now, if you move from that position, then obviously you are creating some energy, or you are generating some extra energy into the thing. Okay, just give me 1 minute. Okay, so let me go back to the slides. Okay. Hmm. So this is an example of the Woodside structure. And as you can see, these are the axis. Let me pick up my pointer. Laser pointer. Okay. So these are the three different axes of the unit cell. So A and B are 3.25 approximately angstrom. And then in this one, the C axis is a little longer because there are more atoms to be accommodated inside the repeatable unit cell. And you can see the each zinc is being surrounded by 4 oxygens, so it has a tetrahedral structure. Okay, so tetrahedral means there are 4 sides of this structure. Okay, now if you look at the bond lengths, okay, you will see that the bond length and the bond angle, there are 2 different angles in this structure, and the one of them is 108, that is in between this is the C axis, is along this direction. So amongst the C axis and the AB plane oxygens, you have a degree angle of 108.27. And there is the bond lengths are also different. These 3 bond lengths are same, 1.975, but this one is different. Okay, so this is the peculiarity of the Woodside structure. Okay, now when you see from the top, you can see that there are 3 triangular forms. Okay, uh, one one is centered with this zinc, the next one is centered with this oxygen, and then this one. So you are putting triangular things. So this is a triangle, this is the triangle. Actually it is a pyramid type structure, so you are putting pyramids one on top of each other, but the atoms are falling on top of each other in a chain. Okay, now when you go to the zinc blend, what you actually do, you turn the pyramids by 60 degree. Okay, so this atom was falling on top of this atom. Now it has rotated by 60 degrees. Okay, so this is the zinc blend structure, which has a different sets of ABC values, but this is a cubic structure. All 3 axes lattice parameters are the same. Okay. You will notice that the bond lengths have also increased. Okay, so 2.345. Okay, and but what is interesting, this angle, the angle, all the angles are the same. Okay, there is no difference in the angles. Okay, now as I said, if you pressurize this structure, the Woodside structure, you can see then you are bringing these 3 oxygens to the plane of this zinc, and then you can move on to a structure which looks like this. Okay, so this will move to that. So if I go back to the Woodside structure, I want to tell you something very interesting here. So if you see, these are the oxygen atoms, and they form a plane. Okay, and then the zinc atoms, they also form a plane. They are separated. They are separated by a distance. Okay, so intrinsically, the Woodside structure has the negative oxygen plane and the positive zinc plane separated by a distance. So that makes it a dielectric material, maybe with some little bit of properties of ferroelectricity. Okay, so that's why it's very important structure, and we have lots of papers on these things, these aspects. Now, if we look at the Roxal structure, we can see that the negative plane, oxygen plane, and the positive zinc plane, they are on top of each other. They are mixed. So there is no spontaneous dielectric constant. So the polarization is not there. Okay. Okay. So let me go to the preparation techniques of these things. So there are several ways of making zinc oxide. So some people can mix. So if you want to modify the chemical composition of zinc oxide, then you have to take two different materials and then grind them. And this is the old way of doing it. You can grind them and mix them properly, put them in contact with each other, make sure that the particles are very small, and then you put them in a furnace where it heats up, and then there is diffusion of ions from one particle to the other, and you grow it a modified zinc oxide. Okay, so this process needs repetitions of grinding and heating. Okay, now even then you will not be able to achieve the best compositions, because how the particles have migrated from one domain, one particle to the other particle, that is a question mark, and you may land up with different types of gradient inside the modified material. Okay, of gradient of what? Gradient of the dopant. Okay, so if the percentage of the dopant is different at different parts, then the physical, the bond lengths and other things will differ. Okay, and as a result you will get different functionalities at different parts of the material. Okay, so the properties of these solid state grown material, solid state reacted materials, are such that there can be ambiguity between two different preparations. Okay, to overcome this problem, people at first thought that we'll go by melting the entire thing and then mixing it up, which is a very difficult process. But then some ideas came in where liquid-based preparation techniques were taken. So the two of them are hydrothermal and solidal processes. And I'm not going to the hydrothermal process because although I grow hydrothermally grown zinc oxide, modified zinc oxide, but there are a lot of ambiguities in this process, because whatever materials you are providing, whether the entire material is reacting inside it is not a sure guarantee. So we may arrive at a modified thing, but how actual is the doping concentration is not very specified in these materials. And on top of that, the condensation may also happen in both states. Suppose you want to dope nickel in zinc oxide. So you have to put a nickel precursor and a zinc precursor into the material, into the autoclave. And then once the reaction is complete, you will get some modified zinc oxide, maybe some pure zinc oxide, and maybe some nickel oxide. The percentages may be very low, but even then you will get something. Why I'm saying this? Because when you start looking into the functionality of the material, if there is an impurity phase, you are not sure whether that functionality is from the dopant molecule forming an oxide or some compound, or it is something different. It is an intrinsic property of the material. So this is very important. So because you are all here to listen to this lecture, I hope that you will be material scientists someday. Be sure that if you really want to make a permanent device or something like that, which is long-standing and reliable, the material property has to be very specified. Okay, and you have to know your material, how it is being, and it is to be repeatable also, right? If you make 3 different items and you land up with 3 different compositions with 3 different impurities things, then your research is not going to help you. Okay, and the last one is solidal. I'll define it in the next slide also. So in it has a condensation, which is a solution of precursors in the liquid form, and then we heat the liquid to form a sol, which is a colloidal suspension, and then we go to the gel part. By drying the sol, you make a thick muddy like material, and then when you heat the gel, you get a zero gel, and then further heating, you get a powder. Okay. Now, so the soluble synthesis, because I could not take you to the lab, I thought of sharing some pictures how it looks like. So the solution of the precursors are taken in this. This is the first step, the step one, and then you go to the salt preparation. The salt looks like that. The small yellowish part at the bottom of the beaker, that is remnant. It still is not a gel. The gel will become much thick, and then we go to the further dehydration of the salt provides us the gel, and the gel upon further heating, all these red triangles are symbols of heating. Okay. It produces the powders, and this powder can be brought out, grounded in a mortar, and then it can be put to a furnace where we get, after heating it at 400 degrees centigrade or 600 degrees centigrade, we can get to our desired phase. Okay, and this is the final product. Okay, so all my samples that will be reported here are prepared by this type of technique. Okay. The first thing that we do is to do the structural analysis. Why do we need to do that? Because the structure will tell us whether it is behaving similarly to the parent structure. Okay, if the structure has changed, maybe we are looking at some different type of behavior, but it will definitely not be a doping, the effect of doping. Okay. So a dopant can change the lattice parameters to some extent, but it cannot entirely change the structure of the material. If it is changed the structure of the material, then it is no longer a dopant. It is a new material. Okay. Okay. Now, this is a picture of the instrument that we have in our lab. It's an X-ray diffractometer. And you can see at the bottom part, this is the sample holder. This is the sample holder. We put our sample here. And this is our, so this sample holder is not, there's no sample here now. So once we load the sample, we put the sample holder up. So you see there's a source, X-ray source here, which is in this picture, it is more evident. So this source generates the X-rays. It gets scattered here, and then we get the diffracted rays here, and this is the direction. Okay, detector. Okay, now you all know about Bragg's law. You are in the PhD level, so or postdoc level, so you must be knowing about the Bragg's law. I'm not going to detail on it here, but what we find from the data is there is some crystallographic that when Bragg's law is followed for a particular DHKL. Okay, these are the HKL values 100, 101. For the particular HKL, we have a D value. Okay, well, separation, right? So that will generate a constructive interference and will get a peak. The intensity becomes high. Okay. Now, if we can fit this data to a model which can be generated from a theoretical structure, then we can see what are the changes in the d-spacings and other things. Okay. So from that, we can find out the lattice constants, the bond angles, bond lengths, everything. On top of that, this is called a Rydberg refinement. I don't know whether I didn't get time to set a slide on the Rydberg refinement thing. But Rydberg refinement is something, it's called structural refinement. The Rydberg refinement is a way of fitting some peaks of Gaussian or Lorentzian nature to fit the data. And these peaks should follow the Bragg's law. And so everything is incorporated in it. And we do a chi-square fitting and we get the desired structure. We can replicate, we can produce a theoretical XRD pattern which will fit this thing. So, okay. So you see, this is the Rydberg refinement here. So Rydberg refinement produces this. The red lines that you see here are the theoretical model, and the crosses that you see, these are the observed things. When the refinement is good, you can get a difference between the actual data and the calculated data, which will look something like this. This is a very nice fitting. This is a little bit of problem is here, there, but there are sometimes our limitations, because the real crystal and the theoretical crystal will always be different. Okay. So when we get a good chi-square value, or there are other parameters in Rydberg refinement which I'm not going to talk about here, but there are other parameters which can be looked into, and then we get a good fit. Okay. So from that refined, there is a crystallographic index file that we have to start with, that may belong to the pure system, and then we introduce the crystallographic index file into the refinement process and make the changes whatever is necessary in terms of ABC. We let the software run on it, on the different values that they give increments in the values of ABC and other aspects, and then we find what is the what values of ABC can match these things. So these are the lattice parameters that have been found for one system. I'm not going to detail on many other systems, but just one system. I think this was silicon doped zinc oxide. So we got this type of behavior that with the substitution, where with 3% substitution, this the lattice parameters have increased. Okay. Now, when you put a foreign element, what can be the changes that you can think of? Okay, so let me move out of this presentation here. Okay, and let me show you a little bit of this software, which is very interesting. Not a software, a web page. So this is called Shannon Radii. Okay, web page. So if you see, suppose we are having zinc oxide, right? So if you see, it gives us the different combinations of charge that is available on zinc. So if you go to iron, you will get multiple. So if you go to iron, you can see there are multiple charges that are possible for iron. But let me not go into that. I'll just concentrate on zinc here, and I'll show you. Suppose, say, okay, let me take the case of iron. Okay, so suppose you dope iron. Sorry. Suppose you dope iron in zinc. Okay. Now, as I said, that zinc in zinc Woodside structure is 4 coordinated, right? That it is connected to 4 oxygens. So the crystal radii, that is the radii of the iron, of the zinc ion inside a solid form, is 0.74 angstrom. Okay. Now, when this is so, I have to see what iron can be very well matched. Okay, what type of iron? Now, if I have a 2+ iron and it is a 4 coordination, the crystal radius is 0.77. Now, if you want to replace zinc 2+ with the iron 2+, this is quite good. Okay, so the ionic radii is a little large. So what will happen? The zinc, which was tightly fitted there, you're putting a little bit higher radius element, so it will try to squeeze out the surrounding oxygens, and that will affect the bond lengths of the zinc, of the metal oxygen bonds, and also the neighboring zinc oxygen bonds will also get affected. So you, by putting a iron 2+ in a 4 coordination system, with a crystal radius of 0.77 have created strain in that particular point of infliction. Okay. So similarly, if you put a 3 plus in the fourth coordination, and you can see that this is 0.63, which is much, much smaller than the zinc 2 plus. Okay. Now, when you do this, what happens? You have incorporated a higher charge element, a ion, into the lattice. The higher charge element is smaller in size, so it has left some space in that lattice. Okay, it has left some space, and it is trying to attract more of the electrons that was present in the oxygen. So what will happen? The oxygen atoms will get attracted more than what it was doing previously in case of zinc 2 plus. Okay, so the bond strengths will become more stronger. Okay, as a result, what happens? And more on top of that, the lattice cannot be charged because you have incorporated an extra charge, extra positive charge into the lattice. What will happen? So it will definitely try to compensate that charge somehow. What are the options? There are two options. One option is it can invite a zinc interstitial, oxygen interstitial, which is a source of the negative ion, negative charge. So in that way, what will happen? The iron, two irons will generate two positive charge, and then that can be compensated with one oxygen interstitial. Okay. On the other hand, it can lose one of the zinc for two iron substitute atoms. You can lose one zinc. In that way, you have compensated the extra positive charge. So by doping something which is not of the same charge and not of the same dimension, you have generated some stress, strain, or defect states into the crystal lattice. So I believe this is clear to you, because the next thing that I am going to do is show you some results which will be very interesting. Okay. Okay, let me go back to my presentation as of now. So the strain that I talked about can be easily calculated from Scherer's formula. There's a process of doing this. So there are the crystallite size can be calculated from Scherer's formula, and the strain can be calculated from the Williamson-Hall plots. So we modify the data that XID has given us, and we take a definite theta where the peak is there, and then we can plot this type of data, and then we can find out the induced strain and the particle size, how it. So interestingly, it has been observed that if the strain increases, then there is a decrease of the crystallite size. This is not just in one case. Most cases are like that. I am not saying that all cases are like that, but in most cases, the strain actually reduces the crystallite size. Now the question is why? So if you think of it in this way, what is strain? It is a extra energy that we have fed to the lattice, which is restricting the order of the lattice. Okay. So when you restrict the order, then you are trying to pull it or stretch it to a point where the structure will say, okay, my God, I have tolerated enough. I have to now stop this nonsense. Okay. So they will cut short and the lattice crystalline size will reduce. So this is a common experience in most doped materials. Okay. So if the strain is too much, then the crystallite size becomes much, much smaller. So you understand that if you can modify the bond length, bond angles, and then the lattice parameters, obviously, and then the strain in the lattice, and also control the size of the material due to these things. Okay. Now, every material, to be understood properly, we need spectroscopy. Okay. We need spectroscopy, and in the spectroscopy has different forms. Okay. It can be there in all spectroscopy, there is a source of excitation, and that excitation will give us some information from the material, because that excited energy will generate some type of transitions inside the material, and as a result we will have a different response in and if we can analyze that response, then we'll know about the material much more than just by seeing it. Okay. Now, we all know that materials are composed of atoms, and atoms have different energy levels. It's not only atoms, it's a molecule, so there may be different types of vibrations involved. There may be different types of rotations in the molecules, and then there can be the latent, the energy associated with the formation of bonds. All those types of things are involved in these things. Okay, so you can have you can shine different wavelengths and see what wavelengths are being absorbed, and by analyzing those absorption energies, you can assess what type of material it can be. Also, if you know a material and if you doped it and modified it, you can also find out what type of changes has been brought up by that doping. Okay. So there can be fluorescence, direct fluorescence spectroscopy can be done, absorption spectroscopy can be done, and then phosphorescence spectroscopy can be done. And then there is Raman. I'll come to it later on, but this is very important because in Raman, what happens, the vibrational states can be understood by exciting the material to a higher virtual state from which it can transit to the original state or a state up above or below. The states that I'm talking about, the actual states, these are vibrational states, and these are due to the phonons, the vibrational aspects of the material. So every vibration is associated with the energy. Those states are depicting those energies, and any transition between these states can be recorded by Raman spectroscopy. I'll come to it later on. I hope Rajesh has taken a class and you have understood Raman spectroscopy well enough. So I'm not going to detail it in this slide. Sorry. Okay. Now, X-rays and electrons are very important to analyze materials. Okay. Now, when I say this, I just want to make sure that you understand why X-rays and electrons are considered as one of the very important things. Neutrons also are very important, but neutron spectrometers are not very common, and it's very highly in demand, but it's not everywhere available, and is very costly to run also. So we have resolved to X-rays and electrons. Okay. Even electrons, when you talk about electrons, electron microscopy is very costly. So comparatively, X-ray is the better way of looking into materials. Now, why is it so? The X-rays have wavelengths which are compatible. X-rays, electrons, and neutrons have wavelengths which are compatible to the atomic or the molecular dimension. Okay. So if you suppose I give you an example here, suppose I give you a flat surface which is filled up with marbles, which is closely tight packed with marbles. Okay. Now, if you want to understand how the surface is looking like, can you judge it with a tennis ball? Means, if you bounce a tennis ball on that surface, will it, from a definite angle, will it scatter in different directions? It will not. It will think that it is being scattered from a plane surface, because it will consider the entire surface to be a plane. Okay, because it is much bigger dimension. Okay? But if you do the same thing with small steel balls, which are made for ball bearing of cycles and other things, right? Definitely it will hit those marbles and fly off in different directions. When you can make the material scatter in different things, then we can see the material. Okay. So, and an example is, if you shine light on a mirror, that's why, in a cinema hall, the curtain is definitely not a flat surface. Okay. It's made rough for this reason only. So you have to resolve, you have to make the light fall and scatter in different directions to analyze what is the topography, what is the difference of intensity that is coming out from that surface. Okay. Now, X-ray fluorescence. So X-ray is one. First, I'll talk about I explained why X-ray and electrons are important. Now I'll tell you how X-ray can be utilized to do different types of measurements and to understand the microscopic and the microscopic parameters. Okay. Now, one thing is the X-ray fluorescence. Okay, what is X-ray fluorescence? You shine X-ray on a sample and you take the information out of it. What happens? The X-ray, if it is quite high in energy, it will go and hit a core electron out of the orbit. Okay. So when the core electron is, this core electron, sorry. And the core electron is ejected from the material, because this X-ray has the energy which is enough to throw the electron out of the thing. Okay. Then what happens? The electron goes away, and another outside electron that can go and fill up this place. Like this one, it goes back to fill up this place, and X-ray is generated. The energy gap between these two orbits is corresponding to the X-ray, to an X-ray. And this is a characteristic X-ray. It is not any energy, because the electronic orbitals are fixed, right? So whenever this phenomena happens, you knock out one electron from the core level, it will be substituted by a higher energy electron to fill up this thing, and an X-ray will be emitted. By analyzing the energy of these X-rays, you can find out what the element is, because if it is potassium, it will be something. If it is lead, it will be something else, because the energy levels are absolutely discrete for different materials. So if you have a material and if you count the number of rays that are emanating from this material, then you can find out how many atoms of that particular material is there inside that, of that particular element is there inside the material. Okay. So it is a nice way to find out the chemical composition of the material. Okay. So so this is about X-ray fluorescence. So X-ray fluorescence can be done from there are specific measurement systems. Nowadays, XRD instruments also are carrying some of the XRF components. And then you can have the same information from a scanning field electron microscope. Okay. Now, how is it that electron microscopy can give us? Let us understand a little. What is a field emission scanning electron microscope? The electron microscope has an electron gun, and then there are lenses and anodes which streamlines the electrons and makes it fall on the material. Okay. Now, when the electrons fall on the material, They have three different processes. So one process is the primary electron comes and hits the atom, and the secondary electron is emitted. Okay, the secondary electron is one of those k electron, the same mechanism. Okay, instead of an X-ray, here it is the electron of the same energy. Okay, now if you go to this one, the same work is being done by a this thing by an electron. Okay, so the secondary electron, there is a secondary electron detector which can detect the thing. Okay, now there can be a backscattering process also. The primary electron, it does not knock out any electron from the core, but what it does, because it is passing through the um, bypassing the nucleus, it gets bended, the path gets bended. So these are called backscattered electrons. And the backscattered electrons are mostly have a lower angle. Okay. The secondary electrons can have any angle, so you can put a secondary electron at a larger angle. But the backscattered electrons have very small angles. Okay. So because most of the backscattered are coming the same way out. And then there will be the same process that I showed in the last page, that it will generate the characteristic X-rays. Now, by generating this characteristic X-rays, you have generated a spectrum. So you can know how much of iron or how much of zinc you have put in the zinc oxide. Okay. So this is a effective way of knowing what is the percentage of doping. But let me warn you here that this data is not absolutely trustable, but obviously you can find out a qualitative um, estimation of what you have doped. Suppose you have doped 1.5% and you're getting a 7.7%. It's not end of the world. Okay. So you have to check whether the 1.5% is giving 0.7 and 3% is giving 1.5%. If that is so, you have to be happy. That is the limitation of this technique. Okay. Now, scanning electron microscopy is done to the important aspect of it is to find out what the morphology of the material that you have prepared is. When you say the morphology, I'm talking about when you start confining a material from bulk is monotonous. Okay. But even bulk has certain aspects which we can look into. But if it is nano or micro in size, then there are aspects where you can put your mind into and see what are the differences between two different materials which have been grown with a slightly different aspect. Okay, so morphology can be changed due to the atmospheric oxygen that you have used in the material in the synthesis process, or it can depend on the amount of dopant that you have put, because the dopant can create strain and then it can terminate a lot of surfaces, which I'm coming to the next slide on. And it can also give you an estimation of the chemical homogeneity. This the FASM. We call this data, this part, the characteristic X-ray part, energy dispersive X-ray spectroscopy. So we can take the example. This one example is of silicon gallium doped zinc oxide, and you can see that you can check the composition. Here you can see that the gallium is there and silicon is also there. In this compound, there is no gallium, no silicon. Okay. The composition, the dopant percentages that we used obviously was not the same as we got the result in, but that is understandable because there are lots of problems in this technique. Correct estimation is not possible. Okay. But what you can do is you can check the chemical homogeneity of the materials. Okay. So what do you mean by that? Suppose this is the zinc oxide, pure zinc oxide, right? Here you are expecting zinc and oxygen only. So you can see the zinc is everywhere, right? It's everywhere. Like here, there was the sample looks like this. I do not have a picture of the sample at this moment, but the sample had a hole here. Okay, so you can see that it has more or less depicting how the zinc is sprayed all throughout the surface. There's no difference of the intensity of the thing. And similarly, wherever the zinc is maximum, oxygen is maximum. So this confirms that zinc and oxygen are in equal distribution. Okay. Now, in case of dopant, this provides a very good information. Is the gallium uniformly distributed? Is the silicon uniformly distributed? Yes. So this is the benefit of doing EDX in using a FESEM setup. Okay. So, and then as I told you, let's see this, the structure, the morphology is a very important thing. Okay. You can understand whether a particle, the material, is composed of distinct particles, or it is tied up somewhere like this one. It grows from one definite seeding point, and due to the the ease of growth along some of the directions, it has started growing in those directions. But there must be some seeding point which was multifarious. Okay, means there were multiple seeding points at one point. So that's why they have turned out to be pointing towards different directions. And then there are some small microparticles. And then you can also find see this graph is not fully seen here, but this says that the particle size, mind you, it's not the crystallite size, it's the particle size that I'm talking about. Here, you can talk about a big particle, not a small nanocrystal. Okay. A small nanocrystal, maybe you can judge properly up to 50 nanometer. But if you see that particle, same particle, under an electron microscope called a transmission electron microscope, you may land up into a different analysis. Okay. Because generally what happens, the particle is composed of several grains embedded in the same particle. Okay. In the same particle. Yeah. So there will be the crystallites. There will be crystallites which are adhered to each other in such a way that you will not be able to distinguish it by SEM. Okay, by scanning electron microscope. But once you do a transmission electron microscope, which is something like that. So it is same principle is there. Only the electron beam transmits through the material. So if there is a small nanoparticle, which it can penetrate through, the electron will pass through and it will suffer a interference pattern, which can be Fourier transformed into a real space, and we can get an idea of how the atoms are separated. So this is one of the palladium metal electron microscope. This is a very favorite picture of mine to explain transmission electron microscope, where you can see that there are two crystals. The crystallites. Okay, this is a part of the same particle, but you can definitely see that there is one crystallite here, another crystallite here, another crystallite here, another crystallite here, and there is a separation in between which demarcates the domain of one crystallite from the other. Now, so in our samples, let us show how zinc oxide also shows the same thing. Okay. Now, from the FESEM, we found that the particles were about 100 nanometer to 50 nanometer in size. Okay. That is also seen in a normal TM picture, where we can see the particle size. We put it in a software called there are lots of softwares actually where you can find out the particle size. Okay. So, and then in transmission electron microscope also, you can do a EDX, and you can find at the atomic level what is happening with the homogeneity of the material. Okay. Now, if you see, there are high resolution atomic distributions in the material. Okay, so if you take this if you take this thing, sorry, let me so this software, I don't know whether I have the image right now. So this is image J. You can upload, open. No, I don't have the images now here. Okay, sorry. So one of these images can be uploaded, and I should have been able to show you. Just let me take a little bit of time to see whether you haven't that field. No, I don't have. Sorry, this is not there. So I cannot show you at this moment, but I wished I could show you. So this images software, we can load the image, and you can find one of those domains that you are interested in. Okay. So this part has been enlarged in this image. And what you can see that there is a regular array of atoms, which says that this material is perfectly crystalline here, or very well crystallized. Okay, but when you go to a doped system, the same thing you can see that due to the doping, there is a termination of the crystallite. There is a termination of the crystallite. This is what I was talking to before. Okay, the termination happens due to the strain that we have seen that can be generated by a dopant. Okay, so the crystallite sizes that are there, they reduce due to these actions. Now, very interesting. Now, if you see this type of regular domain, you can Fourier transform this image and get a diffraction pattern using that image software. Okay, and from this diffraction pattern, you can calculate the despacings and also do the same analysis that you have done in XRD. Okay, so transmission electron microscope and XRD are complementary to each other, but people do that to show that the atomic, the structure in the atomic level, in the molecular level, is the same as the average crystallite thing. Okay, and I believe I have told you about the strain and how it can be seen. So all these strain generated things, or the boundary, the grain boundaries, or the terminating edges. Sometimes what happens, I don't have a picture right now, but if necessary, if anyone interested, you can contact me. I'll show you some of the images where the grain boundary termination of the grain boundaries happen. That you can find out by having a better resolution image of this one at the edge, and then finding out the distance between the atoms. And from the distance of the atoms, you can find out what despacing is commensurate to that separation. Okay, and then we can find and analyze that the crystal has terminated at this edge. Okay, so what can we learn from HRTM? We can have a crystallographic study of the crystallographic faults at the atomic level. You can have an idea of the crystallographic structure at the atomic level, crystallite size, grain boundaries, terminating edges, chemical composition, homogeneity, morphology at the nanoscale. Okay. Now, as I said, that the valence state of the dopants are very important. Okay. Now, how to be sure about the valence state of a dopant? In a zinc oxide, okay, if I take a parent host, we know that zinc is in 2+ state. Okay. But if it is in any other state, suppose instead of zinc oxide, we take copper oxide case. Okay, so Cu can occur in Cu2+, and it can also occur in Cu+. Okay, so if it is Cu+, the chemical compound that will come up is Cu2O, and in if it is 2+, then it will be copper oxide CuO. Okay, the structure is totally different in these two materials. Okay. So if you take out the oxygen, and if you out of the box here, I'm telling you just to give an example, the lattice vibrations are also different. Okay, why the what is the difference? In one, the oxygen molecules are the ones which vibrate. In the other one, the oxygens are still, but the copper vibrates. So you see that by changing the structure, you can bring in a lot of change in how the material behaves. So that's where the charge aspect of every dopant is very important, because it is related to the ionic size, it is related to the ionic charge, which is further related to what defects it will create in the lattice, what strain it will create to the lattice. Okay. So the X-ray photoelectron spectroscopy comes in very handy here. So it has some excitation. It can be an X-ray tube producing X-rays. It can be a synchrotron source producing X-rays, or any other light which is capable of ejecting photoelectrons from the surface. It can be a laser. It can be a UV lamp or whatever. But it has to eject photoelectrons from the surface of the materials. Okay. So this is a famous photoelectric effect that Einstein worked on. So it uses the same principle: shine some light, eject some photoelectrons, and analyze the energy of these photoelectrons. So by analyzing the energy of the photoelectrons, you can find out, you know, the energy of the incident light. So you can find out what are the binding energies of the surface atoms. Okay. So whatever elements are present on the surface, what are the exact chemical composition and their characteristics? I'll come to this one later on. Okay. So in this equation, this is a very well-known equation, so I'm not going into it. So what it does, it ejects the same free electron out of the thing, and instead of analyzing the X-ray here that is emitted, we are analyzing the energy of this electron, and that from there we are calculating the binding energy, which is a characteristic of the elements that are present. Okay. Now that gives us a huge benefit, because what you can see in this case, this is one very nice case that I want to describe here. So we took 4 different compounds and 4 different material, the same dopant, but in 4 different things. Okay. And you see the oxygen, which is bound to the zinc oxide atom, the material, has 3 different binding energies, which can come from 3 different types of oxygen. What do we mean by 3 different types? So some oxygen can be a lattice oxygen, which is well placed in the lattice. Some oxygen may be a vacant oxygen space. So there is no oxygen, but one oxygen was supposed to be there. Now that will also have a energy, particularly when it comes to an electron emission. Okay. So there will be certain amount of charge left in that void, so that electron can also be emitted. Okay. And then there is a chemi-absorbed oxygen. It is not part of the structure. It is just sitting somewhere on the surface. Okay. Now those energies will be different. The chemi-absorbed ones will be somewhere here. Yeah, and the lattice oxygen is here, and oxygen vacancies will be here. Just give me 1 second. Shwebal, আমি লেকচারে আছি। বিজ্ঞান ওকে, জাস্ট give me 1 second. আরে শ্রীমন্তর এটাতে আছি, আমি কথা বলছি। Okay, so by taking the XPS data of these samples, we have found out that in some the oxygen vacancies have increased. Okay. Now this was a lithium doped sample. Okay, so as you dope lithium, you can see that the oxygen vacancy content has increased. Okay, so it's obvious because you are putting a lesser charge, so it cannot retain all the oxygens that it used to. So depending on the percentage of the oxygen, it has increased the oxygen vacancy intake. Okay, now similar to this data, the XPS data, some of us who are acquainted with the beam lines in synchrotrons also do X-ray absorption spectroscopy. X-ray absorption spectroscopy is a similar process. You shine the atoms with a high energy X-ray, and then you analyze the data. Okay, so whenever there is an absorption, there is a peak. So this is the normalized absorption. Okay, so what do you mean by normalized absorption? You are shining the energy, the X-rays on the sample. As long as the energy is not sufficient to um, to be absorbed, it will have zero absorptions. So everything will be transmitted through, okay, or reflected. But the moment you see that you have put the energy which is equivalent to the core energies of the material will be absorbing the X-ray. And when it absorbs, it does two different things. One is it transmits all the other energies, and the other thing, it radiates the same energy due to the transition of an outer electron to the lower electron. So you have an X-ray which is emitted and scattered in all directions. So if you put a detector at some point, then it will be able to take that fluorescence spectroscopy. Okay, so it can it's the same process that I discussed few slides before. Okay, so the energy is being released. You can analyze that X-ray and find out what the energies are. The other thing is the absorption. The absorption spectra is here. So it will absorb at a particular edge, which is belonging to a particular element. Okay, in this case, I'm showing the absorption of a vanadium ion. Okay, so you can see there is a vanadium ion absorbing the thing. So this part near the edge, okay, near the edge, X-ray absorption near edge spectroscopy is called ZnO, and the extended part after that is due to the interaction of the emitted scattered X-ray with the neighboring atoms. So what will happen? It's like a ripple on the, you throw a stone on a pond, it will go, and if you have other obstructions on the, suppose you have bigger stones coming out of the surface of the water, at some points, the ripple will go and be reflected from those things, scattered from those things, and come back. And you will soon see the surface of the water has become an interference playground, right? So this phenomena is observed in X-ray absorption spectroscopy too. So in X-ray absorption spectroscopy, we see this interference effect in this EXAFS part. So we take this energy part, cut it out, we convert the energy scale to a momentum space, momentum scale, and do a Fourier transform to a real-time, real space. Okay. Hence, actually what we are doing, we are trying to find out the interference due to the path differences between these two, travel differences of the wave in between the neighboring atoms. So the important part is the distance between that the wave sees, the average distance that the wave sees between the nearest neighbors, nearest scatterers. It also depends on the scattering elements that are present along with the vanadium. But in most cases, if it is an oxide, we get oxygen here. So we get the complete information of what the local neighborhood of that particular ion is. Okay. Now, that's a very powerful tool to understand whether the structure that we are seeing is actually correct or not. Because you can calculate the bond, you can again take the crystallographic index file, feed it to a model, and check the lattice parameters, the bond angles, bond lengths, everything, and infer that yes, it is the same structure. So X-ray absorption spectroscopy has come up a long way since the last 20 years, and we are now looking into the structures from a real atomic point of view. Okay. So in this one, I'll show you the effect of vanadium in zinc oxide. So you can see that vanadium 4 plus and 5 plus, there are two compounds where the vanadium is in 4 plus and 5 plus configuration. And from this configuration, you can see that the edge are differently placed. So if it is a 5 plus, the edge will be at a higher energy. And if it is a 4 plus state, the energy will be of absorption will be at a lower energy state. Okay. So by analyzing our material, where it is close to, we can find out the amount of vanadium 4 plus concentration as compared to vanadium 5 plus concentration. Why is it important? Because if you have a mixed percentage of vanadium 4 plus and 5 plus, the charge state that you are changing in the material will be different, and as a result, the oxygen coordination will the electronic clouds along these dopants will be different, and it will lead to different electronic properties. Okay, so let's go to more simpler things like the UV visible spectroscopy, which is mostly available in all labs. So when we do UV spectroscopy, UV visible spectroscopy, we have a source which passes through an entrance slit to make the thing a little streamlined. Let me ask Srimanta. Srimanta, I have crossed 5 o'clock.
Thank you, sir. Yes, you can continue. Not an issue. This is the last session. Yeah.
Okay, because I have still a lot of slides. Is it okay?
It's okay. It's okay. You can continue. Whatever. Okay.
No problem. Okay, thank you.
Okay.
Okay, so so the UV visible spectroscopy has a source which then there's an entrance slit. The light is streamlined here. Then we have a dispersive device. It can be a prism, it can be a gratings, and which disperses the white light or the UV white light combination to different colors. And then we have an exit slit which chooses the frequency. Now the dispersion device can be rotated to make the different wavelengths fall on the slit so that we can get one at a time, one wavelength at a time falling on the sample. And then there's a detector which can give us the information of what wavelength we are getting what absorption. Okay. Now this absorption spectroscopy can be translated into a format which is called tau plot. The tau plot can differentiate the direct band gap and the indirect band gap by putting the power here. It is 2 in case of direct band gap, and for indirect band gap it is half. I am not going into the theory part today because it will take it much longer. But from this we can find out the band gap by extrapolating the slope of this edge where it comes down. Okay, and it comes down to some value which is crossing the x is equal to 0, sorry, y is equal to 0 plane, and we get the band gap from here. Okay. Similarly, in case of indirect band gap, we have a alpha h nu. Alpha is the absorption coefficient, and h nu is the energy. Okay, so we multiply these two factors and then square it, or make it to the root, make a square root of it and find out this thing. Okay, now in this way we can find the band gap of the material. I'll come to the band gap results later on, how they change with composition. But let me also tell you about the other aspect of electronic material. So why do we do this invisible spectroscopy? Because in most of our semiconductors, our energies that are that separate the valence band and the conduction band are in this region. Okay, either it is in the UV or it is in the white band region. Okay, white light region. Now that's why we come to, okay, where is that slide? I do not know. Okay, let me, no, I must have missed it. Sorry. Once you find the band gap, then you also need to know what other effects of doping can be there. Or even if I say not doping, something internal problem in the lattice itself. When I say so, what do I mean? Suppose when you are making the material, you have treated it in an oxygen-less atmosphere, or maybe minimized oxygen atmosphere. Okay, what will happen? There will be oxygen defects in the lattice. And when you have oxygen defects in the lattice, that will definitely not remain as such. It will also give you some oxygen zinc defects, because it has to compensate the charge somehow, right? The lattice cannot be charged, right? So if associated with the oxygen defect will be a zinc defect, or it can be a zinc in an oxygen place or oxygen in a zinc place. These are the latent defects of a zinc oxide material. Okay, there are other ones also, like zinc interstitials or oxygen interstitials. I told you about zinc interstitial before. Oxygen interstitial is also possible if there is a mismatch of a difference in the lattice formation. Okay, suppose it make it a little less crystalline, you can definitely put an oxygen interstitial. There can be other reasons of oxygen interstitials also. Okay, now let us come to the doping case. Okay, suppose you have a zinc oxide, you have a transition from the valence band to the conduction by illuminating it with some light, and then when it comes back, it radiates the same light, which corresponds to the band gap, right? So that's a near band gap emission. Okay, so here you can see this is the place where you expect the band gap to happen. So it's about 370 or something like that, which corresponds to about 3.125 electron volts. That is the band gap of the zinc oxide. Okay, now when you dope these things, you can see that there is changes in the NBE. This is called a near band emission. Okay, I'll come to this later on also. But along with that, you can see that some other light is coming out. And this other light is not due to a clean crystal. If you have a clean crystal, when with no defects, you're not supposed to get any emission other than the band gap, right? But if you have these intrinsic defects like the oxygen vacancy or the oxygen zinc vacancy or the zinc interstitial, oxygen in zinc place, zinc in oxygen place, you will land up with different types of emissions. Okay, and that can be promoted or demoted by a typical type of doping, putting a different dopant in the material. Okay, so that will come to a later stage, but this is what is happening here. So you excite the electron from the valence band to the conduction band. There can be shallow donor levels, there can be acceptor levels near the valence band, and then there can be zinc vacancies, and then can be zinc interstitials, and it can the electron which is pumped here, it can come down to these shallow donors or the zinc interstitials and transit from here and give the light which is not exact the same as the conduction band to valence band transition. Okay, so these are the lower energies which are here that can be found out. So this is a way to find out what defect states and how much of these defect states are there. This is actually a very nice instrument. I have used this instrument while I was in Milwaukee. So I'll briefly explain the instrument so that it becomes easier for you to understand. There is a detector here, but there is a light source here. So the light falls onto comes through different monochromators, and we choose the right in illumination to fall on the sample. This is the sample chamber, and you can put your sample by taking out this lid. There is a sample placed at 45 degree to this thing. This is the same face that in the middle of this chamber you have the sample, and it throws out the light which is in the fluorescence mode, and it has a slit here, and there is another monochromator, and after the monochromator it passes through to the detector, and then we get this data. Okay, now let me explain the techniques, then I'll just go to this. Okay, now let me see. Okay, so this is an example of the defects state analysis of using photoluminescence. Okay, now you see, as I said, the excitation photon, it goes up, and then non-radiative. These are excited states. It may or may not correspond to a real state, but it can come back at any point to the conduction band and through a non-radiative decay. And then from the conduction band, it can have a near band emission, and also it can have different transitions which correspond to the deep level emissions. So these are the deep level emissions. These are the near band emissions, and you can see just by doping. I think this was aluminum doped. Yes, this was aluminum doped. Yeah. So you have suppressed the emission here, and it is much suppressed here, and then you have a different type of blue type of emission at this point. Okay, so this all depends on how much the defect levels are being modified. Okay, so when we see a data, what we have to have an educated guess of what is happening in the thing. Okay, now what do I mean by educated guess? Now theoretically and experimentally, there are lots of papers which have related the different types of defects that can happen in a normal zinc oxide. Okay, now these are the latent defects of parent zinc oxide. So you can see there are different transitions belonging to different energies, giving different colors. Okay, to defect. So these defect will be suppose responsible for the red orange. So oxygen interstitial is well known for an orange red emission. Okay, like the zinc interstitials will be responsible for a violet emission. The zinc vacancies will be responsible for a blue emission, and similarly the green will be responsible for a oxygen vacancy. Okay, so now if we can check what are the different energies that this spectra that you have got can be given to, so you can have these energies and then fit the data with those known energies, and you can get a data which can imply what type of defects are there in your material. Okay, so this is what we do in our lab, and we get the data from somewhere else, but we analyze the data, and then we can put it into a quantitative comparison. So you see here we have put the UV emission as 1. This is a normalized data. So UV emission as 1 because we know that the UV emission is responsible for the conduction band to the valence band thing. So it is something which is latent to the thing, and it is expected. So if we have compared the other transition probabilities with respect to the transition probability of a band-to-band transition. Okay, and we have seen that with this substitution, all the other defects have really become less. So this is very interesting. So by substitution of some dopant, you can reduce the defect states. Okay. Similarly, if there are examples where you can increase the defect states, depending on the functionality that you want to achieve, you can dope your materials in that way. Now, let me show you this graph. Okay, this is called a CIE graph, and the x is equal to 0 sample is here, and then as you go higher in composition, this is about the luminescence that is coming out as a whole. It is no longer individual luminescence. So when you get the luminescence, you see a color, right? So what is the color? That analysis is being done here. So you can see that originally it had a yellowish glow, but then when you doped this material, whatever it is, the dopant, it went to a red emission. And then as you increased the amount of doping, it went on moving towards a white region. So this material can be used for a white light emitter, and this light can be used for a red light emitter. So this is the beauty of doing this study. Okay. Now let us go back to this thing. Okay, yeah, sorry. Okay, yeah. So this one. Okay. Now, apart from the latent defects, what else can be done? Okay. Suppose you dope something like samarium. Okay. Now the samarium, what are the origins? Prashant, yeah. What are the origins of these bands? Okay, the bands are basically due to the bonding energies that are due to the different hybridization of the atoms, right? So of the ions involved. So if you change the separation of the ions, these energies will be different, right? Now, so when you dope something, that dopant will have some interaction with the neighboring oxygens, so they will determine a different set of energy values. Okay, and these energy values in the band diagram will occupy different energy positions, and accordingly you may land up into different types of defect states within the band gap, or in the conduction band maybe, or somewhere else. Okay, or in the valence band. Okay, so here is an example that you can have a lot of different type of transitions that can happen in between these possible electronic states of the dopant atoms. So not only we look into the latent states, but we can also have newer states that are generated due to doping. Okay, so this is how we try to analyze. So that's where a theoretical analysis becomes very important after we get the data. So we can always look into the material and judge it from the latent defects, but not necessarily it is always true. The proper understanding of the material needs a theory-based experimental work. Okay, now let us move to another type of spectroscopy, which I discussed before, also Raman spectroscopy, which is the vibrational aspect of the material. So in this, it is well known that atoms are vibrating in this material at a finite temperature. All atoms are vibrating in the material. So all vibrations means a to and fro movement. So it can be compared to a spring and ball model. And the spring, being a spring, it will have some elastic properties, and those elastic properties will be reflected in some way in some absorption spectra. Now, what does it mean? So there are vibrational energy states which are responsible, which are corresponding to different frequencies of energies between these states, that will definitely correspond to a wavelength that will be absorbed, and mostly it's in the infrared region. And to understand these states, either we can do infrared absorption spectroscopy, or we can do Raman spectroscopy. In Raman spectroscopy, what happens? We excite the states to a higher virtual energy state. So there are no states in actuality here. Okay, so we have excited this state to the higher energy state and allowed a transition to the same excited state or to a different excited state. Okay. To the same ground state or the different excited state. Now, when this thing happens, it is come back to the same state. So the energy that is given is the energy that is back. So it is a elastic type of scattering. So it's this type of scattering is called the Rayleigh scattering. Okay. Now, when you do not have the same thing, you have to excite it to a state, and then it comes back to the next excited state, or maybe another excited state. So then you can calculate the difference of energy in between these two and find out what the difference between these two energies are. By calculating this difference of energy, you can find out what are the vibrational energy states of the material. Now, how does it help? The vibrational energy states, if you have the model of the material, then you can, in that particular model of the lattice, can support only a few vibrations that are possible in that configuration. Okay, and the frequency of these things will obviously be changed if you dope something, because it will involve a different mass. It will involve a different spring constant, that is the strength of the bond between the two atoms, right? So if the strength of the bond between the two atoms are changed, we have a different force constant, right? So, and the force constant will give you a different frequency. Okay, so both the force constant, the energy, the strength of the bond, and also the mass of the material that is involved will give you different types of vibrational spectra. So when you dope something, these things get altered. Okay, and you can check these differences by doing a vibrational Raman spectroscopy of these things. Okay, now this type of absorption and emission process, where the energy of the emitted light is lesser than the absorbed one, is called Stokes Raman scattering, and when it is more, it is called anti-Stokes. Now, incidentally, Stokes and anti-Stokes, there can be intensity ratios, and that can actually give you the temperature of the. So if you increase the temperature, then the intensity of the Stokes and anti-Stokes will change. So, and there's a huge theory on that. I'm not going into the details of this one. Okay, but what does the instrument have? It is a very simple instrument. It has a laser. It's simple instrument principally, but actually technically it is very difficult. Okay, so it has a laser which focuses the laser on the sample. It is mostly in a micro range. Micro part of the sample is monitored, and you can see that the background picture that I have here provided here is a optical image of the surface that is being investigated. And now you can do a 2D scan on this one of the Raman spectra and see whether the different energies that are coming out are really uniform all throughout the surface. So maybe if there's a compositional difference, then you will see different Raman spectra at different parts. So the homogeneity and other aspects of these things, of these materials, can also be. found out. Now, this mind it that Stokes and anti-Stokes are not elastic scattering. These are inelastic scattering, right? So, what is the ratio of the Rayleigh and the Stokes anti-Stokes? If this is 99.99%, this will be 0.001%. Okay. So the Raman spectra is really weak. Now the problem is how to detect it. This is something which C.V. Raman did in a small room in Kolkata, where I did my PhD. Actually, that was not the same building. The building where he did it is a previous starting unit of Indian Association of Cultivation of Science. So he did this experiment in a small room, and he used sunlight, and then he used different filters to make replace this laser here. There was no laser at that time, so he had to put monochromators, and that then focus the light to the sample, and then get the 0.001% of the reflected light. So that's why he had to depend on a very strong source, and what can be a better source than the sun. So that's how he did the experiment, that back in some early stages of 1900s. Anyway, so after this thing comes out, there is a filter, and this filter just blocks out the Rayleigh scattering. Okay, so it is a very low band where it does not allow the light to come out. Okay, so you can see in this spectra, you have a lot of peaks here, right? A lot of peaks, but this peak that you see, okay, let me show one of the, okay. So you see we have calculated from 200 to 800, say, okay, but at 0 there is a, why I'm not showing until 0, because the data becomes very noisy here, because we have cut off with a filter, and only a small intensity that is left, that we are seeing here. Okay, now this is what C.V. Raman did, and we are using his technique to analyze our samples. So you can see the laser goes to a divider, and then it goes to a sample, it comes out, and then it goes to a gray through the notch filter, then it goes to a pinhole, and then it goes to a grating where it disperses, and we analyze the material. Okay, now in zinc oxide there are several important modes of vibrations. Okay, and this one is called A1LO. So suppose this is a zinc, this is oxygen, then the zinc and oxygen will, in one line along the c-axis, will move in opposite directions, and in the same AB axis, you remember the structure, I believe, they will also be in opposites. Okay, and in the A1TO mode, the vibrations are a little less, but you see the energy will be different. Okay, this is at a much lesser energy, and why I call it energy, because it's centimeter inverse, that's a frequency, that's basically it's an energy. Okay, so the E2 high mode is the strongest mode. Actually, here you can see the E2 high mode is the strongest mode. This is the most common mode in zinc oxide, and it is due to this type of vibration. This one goes this way, this one goes this way. These two vibrate simultaneously in the same direction, and these two simultaneously in the same direction. Okay. Now, similarly, E1T mode, and this is actually a little weaker mode, and E1LO modes. Okay. Now, what we do with the spectra, I'll come to the next slide, then you'll understand. Okay. So there is one very interesting feature here. So you can see the difference of the modes also. Okay, there are E2 high minus E2 low. There is a E2 low mode somewhere, and then you can find the difference modes here also. Okay, so that is the beauty of Raman spectroscopy. Even the energy differences can be counted. Okay, okay. I did not show them. Yeah. Okay, so let me explain here. Okay. Oh, yeah, there's a fitting here. Okay, so this is the data original data. And what we have done, we have fitted the data using a software called FitYK. And this FitYK, what it does, it takes out different peak forms, Gaussian, Lorentzian, or Voigt, which is a mixture of Lorentzian and Gaussian, and tries to fit this data. And by fitting the data, you can know what type of frequencies have what type of intensity. So how many modes are activated in that form. So analyzing this data from the area and the peak heights and the full width of maximum, we can see that there can be some red shift or there can be some blue shift if depending on the bond strength and the mass of the dopants that are doped into the material. Okay. So when it comes to a lower energy, it is a red shift. When it goes to a high energy, it is a blue shift. Okay. So this is how we analyze what type of material is really doing what. Okay. Now, if there is not much change in the mass, then it must be due to the strengthening or weakening of the bond. Okay. Now, from this analysis, there is a strain calculation measurement also from this type of data, and then we can find out the strain that is available in different phonon modes. Okay, so in a phonon mode, you need a stretching and or a rotation. A stretching or bending, right? So those type of things has different deformation potentials. Okay, and these deformation potentials can give rise to a in plane or out of plane a strain. So those strain components can be calculated, and in fact, this strain is also associated to the crystallographic strain that is available from our strain calculations from XRD. So maybe they are not exactly the same value, but they are more or less proportionate to each other. So a blue shift generally is associated with the compressive strain, and the red shift is generally associated with the tensile strength. Okay, so this type of analysis can be done. There are two different equations here I have put for two different modes here. Okay. Now this is done. Let me see whether I have missed something here. No, I have not missed. Okay, now talking about defects and other things. Okay, another way of looking into the defect systems in the zinc oxide materials is electron paramagnetic resonance spectroscopy, EPR. Okay, so these are sensitive to different paramagnetic states that are the native defects. Okay, so here you can distinguish between the incorporated defects due to our this thing. What is that called? The dopants. Okay, the electronic states of the dopants, and the original latent one, because those energies will be much different than these regions. So if you look into these absorption, and what happens if you put a magnetic field and electric RF energy, then the RF energy gets absorbed at a particular magnetic field strength. And if you do a first derivative, then by finding the crossover where it crosses zero, you can find the field that is responsible for that absorption. So, and then that can be correlated to the G factor that is responsible for such a thing. And from these G factors, you can find out what type of vacancy is there. So the G factor, if it is 1.96, it is oxygen vacancy with a plus charge. If it is 1.99, it is a zinc vacancy with negative charge. And if it is a normal one, it is 2.05. So by calculating the G value, you can find out what type of defect it is. Okay. Why is it here? Sorry. Okay. So band gap, I already said. So yeah. So let me quickly go through it. The entire energy spectra is there to analyze our samples. Okay. So in UV waves, I already described in that slide. Actually, we generally for solid samples we take the diffuse reflection. What is the difference between the diffuse reflection and the specular reflection? The specular reflection happens at a particular angle, but diffuse reflection is generally happens in all directions. So diffuse reflection is more due to not the plane surface. It's about a more informative about the of the property of the material. So the UV visible spectroscopy is actually limited to this area, means a little bit of UV here and then the entire visible range. Okay, so this is the experimental setup that we have. I already explained this thing, so I'm not going into it. In general, for liquid samples and other samples, we have a reference sample and a real sample, our sample, which we are wanting to see. And then we calculate the difference of the ratio of these two things. Okay. So this is our small equipment where we, but there are optical fibers which goes to shine the samples, and from the reflectance of those things we get different types of spectra. So this is the tau plot that I was talking about. So see here the zinc oxide is coming down at here at this point. So somewhere here somewhere 3.2 1 or 0.5 is the band gap. But as you go with the doping, the band gap has changed. Okay, so it has gone to a higher state. Okay, so if you plot the band gap, we have found that within the error limits, which it is like that. And okay, now something very interesting. So this cubicle now in okay, let me tell you how will you calculate the absorption from a reflection spectra. What we have is a reflection spectra and nothing else, right? So in the reflection spectra, actually you can calculate the absorption spectra from this equation, okay? For A plus T plus R, that is absorption coefficient plus transmission coefficient plus the reflection coefficient is equal to 1. So in a solid sample which is not transparent, transmission is 0. Okay, we can take it to be 0. So the absorption will be proportional to 1 minus R. Okay, uh, somewhat very close. So we can take a square of it and get the intensity of it. And then the scattering capability, if we take the scattering capability, it will be inversely proportional to the reflectivity, right? So Kubelka and Munk developed a function called Kubelka-Munk function, which is equivalent to the absorption coefficient alpha, and that is very close to 1 minus R square by 2R. So this is universally accepted for diffuse reflection spectroscopy. Okay. So now from this thing we can, if we calculate the absorption data and then make a 1 minus R and all these calculations, and then we can get the alpha. Then we multiply alpha h nu and then get this square it, then get this tau plot. And also we also know that at these points, this is not the right one to show, but if we plot alpha, you will see that near the band edge there are carving nature, which is an indication that it should have come down straight, right? It should have come down like that, directly like this, right? Absorption should have taken place immediately after the band gap, but it did not. So it has certain states which are responsible for this tailing of these bands, right? Whenever there is tailing of these bands, there must be some other states which are responsible for this tailing. That means there may be some strain in the lattice which is not exactly commensurate with the bond angles and bond lengths that are responsible for a direct absorption there. Okay, so these defect states will come in handy uh, when you try to assess them through a equation which is alpha is some alpha constant alpha 0 multiplied by this exponential nature of these things. And it is, if you can correlate with the energy of this thing, because this is an energy graph, so it is dependent on the energy, so it is an exponential nature in energy, so there must be another energy which is a which is associated with these states, which is called the Arbach energy. So that is a constant which is representative of this strain. Okay, so by taking log of both sides, you can get at alpha, log of alpha is equal to log of alpha 0 h nu plus u, and this will give you a straight line. So you can see there are straight lines that have been plotted. The white points, the ring points are the experimental data, and the fitted data is a straight line fitted through it. Okay, from from this equation, if you see that 1 by u is actually the slope, y is equal to mx plus c. C is not that much necessary here, but mx, the m is 1 by u. So from the slope, you can find out the Arbach energy, how much energy is devoted to the to this thing. Okay, so you see that we can find out the strain and the defect states from all these type of spectroscopy. Now we'll go a little bit ahead and find out about the transport properties. Okay. Now, when you do the transport properties, you have the to first understand what type of carriers are there in this material. Okay. Now, when I talk of carriers, I can immediately land up into electrons and holes, and that is what generally we see. But there are other materials where ionic transport also takes place in ionic glasses and other things. People have tried to do Hall effect on those things. Hall effect, by the way, I hope you know by this time that is a very effective way of determining carrier type, carrier concentration, mobility, and the conductivity. And also sometimes you can calculate the drift velocity. Some people generally do not report the drift velocity, but the mobility is the more important factor here. But yeah, all these factors can be analyzed here. So those who have not gone through it, there's a quick revise of a BSc subject. So you apply an electric field and generate a current through it, and then apply a magnetic field which is perpendicular to that electric field, and then you can, so the magnetic field is along this direction, and then you can get a voltage because the carriers are deflected due to Lorentz force. Okay, so mind it that the deflection, the force on both electrons and holes are in the same direction, because the force is equal to q e cross uh, um, the current and the magnetic field cross product. So the current will be changed due to the nature of the thing, and the current direction of the current, and the charge will also change. So q and I, that both will change. So that will lead to the same direction of the force. But that will make the electrons move in one direction and the holes move in the same direction. If it is an intrinsic material, both holes and electrons, if and they are both present, they will go to the same thing, but they will neutralize each other. There will be no Hall voltage. But if it is a doped extrinsic type, then the majority carriers will go will dominate, and then we'll find the voltage that has been generated in there. So see, here one I want to show you one example of gallium doped zinc oxide. So zinc oxide is a dominantly electron has a dominant electronic carrier nature. So it's an n-type thing. So when you dope gallium, immediately it becomes a p-type. How do you know? The Hall coefficient is above is more than 0, is positive. Okay, if the Hall coefficient is positive, it becomes a p-type material. So gallium doped materials are p-type doped materials. What is interesting is you not necessarily you put more gallium and get more p-type. The p-type nature has decreased in case of high concentrations of doping. Okay, so what can be the cause? There can be many causes, because more gallium is 3 plus, so it is substituting zinc as in the 2 plus state. So they either they generate oxygen sorry zinc vacancies, which can be a source of the n-type nature. Okay, so all these type of things are there. Okay, now when we come to these aspects, it is very interesting, and in our interest goes into what actually happens theoretically. Okay, so if we calculate the same things in the theory from the theoretical point of view, what will happen? So this is one case where I have co-doped. Okay, so far I was talking about doping, right? Now I when I came to IIT Indore, I thought of, okay, in doping, you have a limitation of doping either a same valence state, so there is no interest. It is because the same type of same type of valence state. So maybe it will just show the same things, only the crystallographic, only the ionic size will be different, so there will be strain and other things that's generated. Now if you dope something with 3 plus or 4 plus, then you will land into oxygen interstitials. That is also, you don't have any control on it. So what about what if you dope lithium or something like that? You will land up into less oxygen, so the oxygen vacancies will be. So these are known type of experiments. Okay, so what I started with here was a co-doping of silicon and lithium. That was my first project here that I started. And why silicon and lithium? Silicon is well known to enhance the transport properties due to the differences of the ionic size, which is very small. Silicon is in the fourth coordination is about 0.48 angstrom, which is much, much smaller than the zinc. But what it does, it has a 4 plus charge state, so it invites oxygen interstitials, or it invites zinc vacancies, right? So this type of thing definitely has its effect on the electronic configuration or the electronic charge distribution of the neighboring oxygens and the zincs. So that is what has been studied in these materials nowadays. So theoretically, if you do a electron localization function measurement things, this is not done in my lab. It is done by one of my collaborators. So they have found out that by doping different, as here I'm showing the nickel and gallium case. It is not basically not the same as what I started with. The silicon is 4 plus, lithium is 1 plus. So if you dope purely silicon, it will be something purely lithium, it will be the other end. But if you have a graduating mixture of different percentages of silicon to lithium, okay, so then you can land up with different experiences of reducing means tailoring the effect of the valence state. Okay, and that can lead to different types of electronic distribution. So that when I started, it was very exciting, and we got a jab out of it by doping vanadium and vanadium lithium. No, the vanadium lithium was published elsewhere. JAP was only vanadium. Okay, but those studies were very interesting, and that has led me to co-doped materials. Okay, so co-doping is a very interesting field where you can run a lot of way of understanding what is going on in the subject in the lattice. Okay, so in this example I'm giving, the nickel and gallium dope both are 3 plus, and Ni is 2 plus and gallium is 3 plus. The electron localization of the oxygen atoms in the plane is very high. Okay, so oxygen atoms get very localized. Okay, so electron transfer does not happen very quickly. Presence of nickel pushes the electron localization farther than the gallium doping. So gallium doping has lesser impact than the nickel doped. So these are two different cases. We are presently working on the co-doped material, which is the work is going on. It is yet to come out. But this was interesting. The nickel arrests the electrons. The gallium is little less. Both are arresting, but gallium is little less. And what interestingly, the electronic polarization of the zinc oxygen, the metal oxygen bonds, are different also. Okay, there is much more high degree of electron polarization in the nickel oxygen bonds. Okay, or the zinc oxygen close to the nickel oxygen bonds. So and then I already talked about this point. And so this increased electron localization actually reduces the mobility and hence the conductivity. So even if I have gallium and nickel combined, the mobility factor gets disturbed due to the nickel thing. So if you want a gallium doped for some reason, but you do not want that mobility, you can dope nickel in it. That is the benefit of going through these studies. Okay. Now, coming to the last stage of my talk, actually, two or three techniques are there. So, some of the work that is important right now that I'm doing partially started, not yet fully put my stress on, is the effect of pressure on the structure. Okay, you remember that I discussed that if the Woodside structure is compressed, it can maybe 10 gigapascal pressure you put and you can get into a rock salt structure. Okay, now that has been experimentally proved. Now, how much is 10 gigapascal? It's about 100 tons per centimeter square. So if you put 100-ton thing on 1 centimeter square, it's a huge pressure, right? So that type of thing, if you can generate, then you can go to a rock salt structure. Now, why we want to go is a different question, but what it gives us is very interesting. Okay, so the indentation hardness tests have been done by one of my previous students, Gaurav Bajpai. He was a mechanical engineering guy, so he did it from his own interest. He found that the formation bond, homopolar energy, heteropolar energy are very much correlated to the bulk modulus and hence the mechanical hardness of these materials. So these studies were published in Scripta Materialia back in 2017. And but now what I want to tell you, this thing I just told, when I apply pressure on a zinc oxide, interestingly the current increases. The current increases quite a lot actually, and the more you have gallium or something like iron, mostly iron, if it is mostly gallium with a little bit of iron, you can still see a lot of change. See, this is a meager current, very less current, and immediately when you put pressure, the current has become so high. So what you are doing, you are compressing this structure to a more flatter one. Okay, so you are decreasing this bond length, you are flattening this angle, so the angle has become flattened here. So this may be the reason why this type of behavior is being shown. So we are now doing a theoretical study on this one. If it is possible, we are sending the sample for our high pressure measurements also. If it is possible, then it will be a very nice study. Now, apart from, so these were all related to the property aspect, which can be put into an application, but I have not discussed about the direct applicability of these materials. Okay, now photosensing is a very important aspect of zinc oxide. You can see that this is the homemade setup that we made in our lab, and this requires an Arduino setup and the Keithley meter, 2450 source meter, and light sources. These are light sources. This is entire setup has been made in our lab, and it is basically the light falls on this material. We calculate the intensity of the light here, and then the entire thing is connected, and then we get this photo response. You can see very sharp response, very quick response of these things. Okay. Now, what happens when you shine light on zinc oxide, electron hole pairs are generated. Okay, so the HNU, and then what happens? The electron hole pair along with the oxygen helps the electron gets absorbed. So this oxygen gets absorbed on the surface. When it gets absorbed at the surface, the hole is only left here. And when you turn off the light, so what happens? The current has increased. The electron has been absorbed. So the electron has been transported, right? So the current increases. Okay. In the dark, what happens? The same hole with the absorbed thing. So there is nothing to prohibit the electron from coming out. Okay. So it's now that the light is off, it has got the freedom, and the electron has come back, and the oxygen has formed. Okay. So we have seen that these graphs that you see here can be fitted with two different types of exponential functions. This is an exponential function, right? So it's of the nature of if we have some constant and deduct exponential function, you will get this type of nature. So we saw that there are not one factor can answer this question. There are two factors. So there are two time constants, tau G1 and tau G2, and two current constants involved in this absorption process. Okay. And these absorption processes have been plotted here. So there is one slow process and there is a fast process. So tau 1 and tau 2 are different. So you can see the fast process, and this is TD, once the decay. So the decay thing here. And this is a fast. So you see, with this doping of this was gallium doped actually. So the time taken to respond has become reduced. So this is a very nice sensor of the light that is being used here. Okay, it can be any type of light, UV light, any particular white light, green light, or yellow light. That's what we have done here, right? We have tested with different types of light. Actually, we have tested with 4 different frequencies here, wavelengths. So there are 2 different processes also. Now, what are the 2 different processes? For every sample, this is different. So how will you interpret it? You have to go back to the defect states and find out which state is responsible for this type of nature. What state is decreasing? What state is increasing? So if it is decreasing, maybe that is responsible for this one. So the intrinsic defects and the new defects that are formed in these materials are responsible for the responsivity of this of the photosynthesis. Okay, so this slide I want to come back later on because this is a thin film slide. But here I just want to discuss it before going ahead. So there was a heterojunction created of zinc oxide and copper oxide, modified copper oxide, and we found that the which one is this one? Huh? So this is the composite structure, the heterojunction. And these are the copper oxide and phenomena and the lithium phenomena. Okay. We also have the zinc oxide phenomena, but I did not put up here due to lack of space. But what we see, this junction creation has enhanced the fastness. The tau has enhanced a lot. Okay. So instead of 129 or 130 seconds, right? We have 17 seconds or 28 seconds. So it's a very fast sensor. Okay. Okay. So, and we developed a band structure also. And this is the thing. When UV light falls on it, there's the electron hole pair generation. Hole is here, electron is here. So the electron gets transported to the FTO, and the hole gets transported to the silver through the copper oxide thing. Okay. Apart from that, we have done some photocatalysis. This is also a homemade thing. So we have a cuvette. We need a cuvette, a translucent beaker. This is a translucent beaker, and a white light source, MB dye, and light intensity meter that I already told it. And we use the same UV visible setup. So the same setup that you used for UV visible thing, we have taken the same thing. We have taken a few we have eliminated the samples for certain amount of time and taken the UV visible spectra. Now, in photocatalysis, what happens in the MB? This is the structure of the MB. When you excite the material with light, the electron hole pair generation happens, and then oxygen again gets reduced to reduced to O2 minus, and then it generates a OH radical. Okay, and this OH radical takes part in the breakage of this bond. So this bond breaks from within, and ultimately the products becomes a carbon dioxide and some other components here. So the last things are H2O, CO2, and simpler. So what is the importance of photodegradation? The methylene blue is a very well known dye, which is used in industry, and industrial people are careless, so they dump these things into the water bodies, and this becomes very poisonous for the fishes and marine life, and also to us. So to get rid of this thing, if this type of materials can be widely made, then it can degrade it in quite a nice amount of time. So you can see that the degradation in zinc oxide has taken place in 3 hours. Okay, so it's about 30%. It's not that great. We are still trying to improve on it, but you can well understand that these things take time, and then we have to find out the right recipe. And you can see this the pure zinc oxide and this S4 sample, they have difference in their activity, right? Okay, so the degradation percentage is we first want an assessment of the concentration that is determined from the absorption. So the ratio of the concentration at a definite time with the initial point is proportional to the absorption coefficient and ratio of the absorption coefficients. So this we can calculate. So we can know this one, and then we can calculate the degradation percentage like this. Okay. We have also done the electrochemical properties in a lab, and that is a very interesting thing. And then it's mostly a Faraday reduction oxidation feature, and it originates from the intercalation and deintercalation of alkali metal, which is in our case we have mostly used potassium hydroxide. So the K plus and the zinc oxide, with the help of the electron, forms a intermediate thing, and then it can be reversed when you put the reverse rate. And then this type of graphs are obtained. We can calculate the area of the graph to find out the specific capacity. And we can see here that this is an interesting graph. This is aluminum doped zinc oxide at a particular percentage. Then we have changed the ratio of the aluminum and lithium. So aluminum is 3 plus, lithium is 1 plus. It's an ideal example of charge balance. See how it is effective. See, here it is 100% aluminum, so 3% doping. Here it is 25% lithium and 75% aluminum. So there is still some existence of an extra charge in here. But here it has by 50-50, it is 50-50. So this thing, the charge effect has reduced. Only that remains is the effect of the size of the materials of the dopants. Okay, and then as you go down, you get this type of degradation in the specific capacitance. So definitely the positive charge of aluminum is helping, along with the mixation of lithium. We did discuss this in our paper, and we found out you can get it on the net from why. So the last thing that I wanted to discuss in the previous one, we're now into the thin film preparations and into the device area. So we have this RS sputter in our lab, where this is, you can see in a RS sputtering what happens. The sputter means stripping off atoms. Okay, so you have a target, which is the material that you want to deposit. You bombard electrons onto it, and then it strips off the electrons and it forms a plasma. And then you can see the plasma here. This is called the plume of the plasma. Okay, so most of the and there's a potential that is given to the substrate holder. This is the substrate. You can see a small glass piece is on the top. So it contains. Sorry, it is a attached to a holder which has a little bit of a charge that can attract these things, and then it forms a very uniform thin film. And this thin film, we put electrodes to find out the conductivity and other properties. Okay. Now, thank you for your attention. These are the I want to thank Karyashala, Vigyan Karyashala, Accelerate Vigyan Karyashala, and Dr. Srimanta Pakhira for giving me this chance to interact with you guys, and also the funding sources, IIT Indore and DST, and all my lab people, including my family, who has always supported me in doing the research. Thank you.